Okay, for section 9.3, we're going to be talking about t-test. Now, this will include both one sample t-test as well as matched pair t-test. The process for this would be the same if you had a one sample z-test, but keep in mind that that requires a slightly unrealistic expectation of knowing the population deviation. So all the ones we're going to talk about will be based on sample deviations, but the steps, the conditions, and all that would be the same for a z-test. The only difference in the wording would be the population deviation would be given, and it would have to be given to you. So an example, first example, a company has decided to develop a new AAA battery that's supposed to last longer than previous batteries, which last 30 hours of continuous use. We're going to sample 15 new batteries. On average, they lasted 33.9 hours, so it is higher than the overall average, but is it higher enough to say that this type of battery is better? The standard deviation of those 15 batteries is 9.8 hours. So we're going to set up our test. So for our state step, we would have to say we wish to test at the 5% level, for instance, the hypotheses where the mean is equal to 30. In other words, they're no better than the old batteries, versus the alternative that the mean is greater than 30, where the mean is the true average lifetime of the new deluxe AAA batteries. Some people found that they liked labeling the type of test up here at the beginning, so you're welcome to do that in the state step or save it down for the plan step like we did last time. For the plan step, we would want to say this is a one sample t-test. Once again, z if I was basing it on population deviation. The sample was randomly selected and can be considered independent since it's reasonable that 15 is less than 10% of all new AAA batteries. The normal condition is met based on a graph. So because we have a small sample size, we cannot use central limit theorem. If it was 30 or more as the sample size, we'd use the central limit theorem to say that the distribution of sample means should be normal, but it's not in this case. So given to us, this is a problem out of the book, you have a dot plot, a box and whisker plot, and a normal probability plot. What we're looking for something is, with a sample size of 15, we would like it to be either roughly linear in the normal probability plot, which there's a little bit of wave here on both sides and in the middle, so you could definitely say that there's some concern from the normal probability plot, maybe even condition not met. Dot plot does not exactly look, doesn't look like it has a normal shape. Box and whisker plot the book offers us, but it's not as reliable because you can see symmetry. Okay, so I can see it's a little bit skewed to the right because this half of the box and whisker is wider or more spread out than the left half, but you can't see the distribution, so I can't see that it has a unimodal and symmetric shape that I would want. Okay, so this is probably the worst of the three options. For our do step, we're going to calculate now a t-statistic because we're talking about a t-test. So the t-statistic is equal to the sample mean, which we were given, minus the population mean that we believe is true, so that is from our hypotheses, over the standard error, which is the sample standard deviation, since that's all we have, over the square root of n. Okay, when we put that into our calculator, we get a t-test statistic value of 1.54. Okay, so t distribution is similar to a normal distribution. Here's the illustration if it would help. So that, along with the fact that we have 15 in our sample, so we therefore have 14 degrees of freedom, we can find our approximate probability. Here's the illustration that the book gives. So I'm going to go down to row 14. Find the two values that 1.54 is in between. So 1.54 would be between 1.345 and 1.761. So here, and then I go up to the top of the columns and I get the estimate for the p-value is between 5% and 10%. So there's p-values up at the top. Here's what that really looks like, a little bit more with the actual table. So here I am on the wrong table. Here is table B, the t critical values. I'm going to go down to row 14 and I'm looking for 1.54. Okay, there's the 1.345 and 1.761. So 1.5 is in between those two, go up to the top, and there is the 5, and then 10% that our p-value is in between. So notice it's not an exact p-value, but it is enough to make a conclusion on. So this is, at the 5% level, would be enough for us to fail to reject, because it's saying the p is somewhere between 5 and 10%, but if 5% is our alpha level, then that would be enough for us to conclude that we would have to fail to reject the null. In other words, we don't have enough evidence to suggest that this new type of AAA battery is any better than the old standard AAA battery. Just like with z-test that we talked about last time, if you had a two-sided test, in other words, if the alternative is a not equal to, the process is still the same. So I would look up the t-value that I got, find the two numbers that it was in between, get the p-value from up at the top of the column, and then I would have to double it. So my true p-value is not in between 0.0025 and 0.001, it'd be between 2 times those two values. So it ended up being between 0.005 and 0.002. Still small enough for us to reject, but it is important to get the right p-value range if you're going to use the formula sheet as your method of obtaining the p-value. If you get a negative value, so for instance, if I'd either gotten 317, it's not that hard to figure out. If I'd gotten negative 317 or negative anything, basically you just look at the positive version. So you're looking at the absolute value of t on the chart. So if I'd gotten negative 3.17, I'm actually going to look for positive 3.17 here. So I probably should have had absolute value bars around this t. Here's another example, healthy streams from page 571. It might want to pause the video here and type in those values into your calculator so you can follow along with making the graph that you need, and in a minute doing the calculator practice. Okay, so we're trying to measure the level of dissolved oxygen in a stream or river. The researcher measures the levels at 15 randomly chosen locations along the stream and given in milligrams per liter. Can we conclude that aquatic life in this stream is at risk at the 5% level? So I wish to test at 5% significance the hypotheses that the null is equal to 5 versus the alternative that it is less than 5. Less than 5 would be where the aquatic life was at risk, where the mean is the average dissolved oxygen level at this stream. We're doing a one-sample t-test. The sample was stated to be random and it can be considered independent since 15 would be less than 10% of all locations along the stream, or equally you could have said, if you think of this more as an experiment, that the dissolved oxygen level in one place in the creek or stream should not affect the level in another place, which is important. If the water is flowing, then you could think maybe it is dependent if I'm working my way downstream, as is the water. The normal condition is met on the calculator. What you would want to do after you have your values in is, I'm going to, after I have my numbers in here, go to stat plot, enter, turn my plot on, and I'm going to choose this last type of graph, that is the normal probability plot, and then hit zoom 9, and there's my graph. So compared to the last one we looked at, it's much more linear. So you'd say that the plot is fairly linear without any very severe outliers. So you could say that this justifies the normal condition. The approximate linearity implies that the distribution is approximately normal. Okay, so once again, box and whisker plot, probably the worst choice. Histogram or normal probability plot would be acceptable. Okay, so here is my calculation for the t-statistic. So the sample average minus the population average that I believe is true. Notice the sample average and the sample standard deviation I can get from one bar stats over the sample size, the square root of the sample size. I get negative 0.94. I'm going to use the positive version of that. One's going to have 14 degrees of freedom just by coincidence. So I'm going to go down to 14 and look for the two values on the 14 row that positive 0.94 would fall between. and it would be between 0.868 and 1.076, which gives me a p-value, pretty high p-value, between 20% and 15%. Since this is just a one-sided test, I do not need to multiply that by 2. Between 15 and 20% is correct. So then we are able to conclude at 5% significance, we'd have to fail to reject the null, and therefore cannot conclude that the dissolved oxygen level in the stream is less than 5%. So good news for the aquatic life. That does not appear to be a problem. Okay. These are not filled in, but what would a type 1 and type 2 error be in this conclusion? Okay, so let's go back up to our hypotheses. Type 1 error is rejecting the null incorrectly. So that would be if I said that the null was wrong, therefore concluding that the dissolved oxygen was less than 5, when in fact it actually wasn't. So if I concluded as the researcher that the dissolved oxygen level is less than 5, therefore the aquatic life in the stream is at risk, when that's not true, that could lead to the additions of unneeded chemicals, perhaps. The researchers may try to raise, or sorry, might try to raise the dissolved oxygen level when it's not needed, which could cause other issues. The type 2 error could be, would if I fail to reject the null. So if I say that it's actually 5 or higher, when in fact it's lower, so that would be the opposite problem. That would probably involve lack of intervention, when an intervention would be needed, throwing off the balance of aquatic life. Sometimes on AP for response, they will then ask, which do you think is the worst case scenario, so you could justify. For instance, I think a type 2 error would be worse, because that would be no interventions being introduced when there could be something that is done. In this case, we failed to reject, so type 2 is the type that we could have made in this case. Okay, with that same data, let me show you how this would look in the calculator. So I'm going to go to stat tests and just do a t-test. Okay, since I have numbers in there, I'm going to use data. If I had just the mean and deviation given to me, I would use stats and fill it in. But if I choose data, the calculator will just need to know what list I have in. I will have to enter what my average in my hypotheses are, because there's no way for the calculator to know that just based on the data. So my mu in my hypotheses was 5. My data are in list 1. My alternative hypothesis is less than. That's what's concerning, is if it's less than 5, and then hit calculate. Okay. If you are using the calculator to get your values for P, you need to record the T statistic, so there's negative 0.94. You need to record the degrees of freedom, even though it does not give it to you directly on the one sample. It will on the 2 sample, but not on the 1 sample, so you'd have to record degrees of freedom of 14, even though it's not on here. And then, of course, the p-value. So it gives a more specific p-value of about 18%. Remember, our chart gave us between 15 and 20, so that does fit in with what we got previously. So another way that you can get your answers. I'm going to skip the pineapple example. If you want another example, you can check out page 574, 575. Take a look at how they get information from a computer printout, because I want to jump down to caffeine dependence. For caffeine dependence, we are interested in whether there is a difference in the depression score of people, whether they are caffeinated or not. So what we're going to do is take a depression score with and without caffeine. This is a matched pairs design, and test whether the average difference is 0 versus average difference greater than 0. Keep in mind it's placebo minus caffeine. That would be suggesting that people are more depressed without caffeine than with. Okay, you would have to put both of these numbers into L1 and L2, then use L3 to find the difference, and do the normal probability plot on the difference. Do the statistics on the difference and the test and the calculator on the difference. Go ahead and try the set for 9.3 and let me know if you have any questions.